Hello everyone. In this video we are going to discuss moving coil galvanometer. It is a device to measure a small amount of current, and we have already studied in the previous video that when a rectangular coil, current carrying rectangular coil is placed in a magnetic field, it experiences torque, and because of the torque it rotates. The angle by which it rotates gives the value of current which flows through the rectangular coil, and by using this principle we are going to find the small amount of current by using this moving coil galvanometer. So let us see how the moving coil galvanometer works. Let us take the diagram of this moving coil galvanometer. You can see here in this moving coil galvanometer, an wooden box is there which has calibration screws to level the instrument. The wire is connected to the point L1, and through this the current flows through the torsion head which supports the phosphor bronze strip. Phosphor bronze strip, it is made up of such a material that the tensile strength is very high, so the weight of the coil attached to the phosphor bronze strip will not be able to increase its length. A small concave mirror is also placed here. When the deflection takes place, then the concave mirror will also rotate. Now you can see here two magnetic poles are present, north pole and the south pole of the horseshoe magnet, which provides the magnetic field here, and a rectangular coil is placed here through which the current flows, and at the center of the rectangular coil a cylindrical soft iron core is taken. Now when the current flows through it, it flows through the rectangular coil and then passes through the spring and then to the point L2. When it passes through the spring, the rectangular coil, it experiences a torque because of which it starts rotating. The amount or the angle by which it rotates gives the indication of the current, and that's how we are going to measure the current. The pointer which is connected to the spring will rotate and show that how much current is flowing through the rectangular coil, all the galvanometer as a whole. So let us further discuss it in details. As per the definition of moving coil galvanometer, a galvanometer is a device to detect small amount of current in a circuit. Now this principle is a current carrying coil placed in a magnetic field experiences a current dependent torque which leads to rotate the coil and produce angular deflection. That's what we have already discussed here. When a current carrying rectangular coil is placed in a magnetic field, it will experience a torque, and that torque will actually depend on the value of current. So the amount of twist produced in the rectangular coil will give the indication of the current. So in a moving coil galvanometer, which we have already discussed here, this phosphor bronze strip has a very important role to play here. When the rectangular coil experiences a torque because of the current flowing through it, since it is hanging through this phosphor bronze strip, the phosphor bronze strip will also start rotating, and a restoring torque develops in the phosphor bronze strip which tries to bring it to the original position. Now the soft iron core which is placed here is also very important. It is because if we take the top view, that is, suppose we consider that this cylindrical soft iron core, this is the top circular cross section we are considering here. Now this circular cross section, if we see it from the top, what we will see is a lines of the coil and this circular part, and this is the circular part which we are seeing here. You can see here, this is the circular part, and the horseshoe magnets, these are the magnetic poles in concave shape. north pole and this one is the south pole. So you can see here the magnetic lines of force here from the north pole and ends at the south pole. Actually they are discontinuous they are continuous in nature, but here we have shown only some portion of the magnetic lines. Now you see, when the coil rotates from the top, when you see it, we will see that at all the positions of the coil, the surface of the rectangular coil is always parallel to the magnetic field. Look at the lines here and the lines here. So it is actually parallel to the rectangular coil which we are seeing from the top. Like here it is WZ, so you can consider this end to be W and this end to be Z. So you can see here the magnetic field is always directed towards the center, and it is always along the radius of the circle which we can see here. And this actually represents the soft iron core, the top portion of the soft iron core. Now what we can say is, at all possible positions of the rectangular coil, its surface will be always parallel to the magnetic field, and this magnetic field is known as radial magnetic field because it acts along the radius. You can see here this magnetic field acts along the radius. And the surface here, because we are seeing it from the top view, this is the top view, so the surface here of the rectangular coil in all the positions will be parallel to the magnetic field. So I hope this is very clear to you. So if this is the condition which is taken in the moving coil galvanometer, then we can say that the cylindrical soft iron core is mounted symmetrically between the concave poles of the horseshoe magnet. This makes the lines of force pointing along the radii of the circle. Such a field is called radial field. Okay. Now why this radial field is required, that you will also understand. But first of all, let us discuss here the value I represents the current flowing through the rectangular coil. A and B are the sides of the rectangular coil. The area of the rectangular coil is given by capital A, which is A into B, and capital N represents the number of turns in the rectangular coil. Now we have taken a rectangular coil where the current is flowing. This is the same rectangular coil which we have taken it out from the we are taking just an example where we have taken the rectangular coil out from the moving coil galvanometer, and here you can see the magnetic field acting on it, and because of the current carrying conductor, we have discussed this in the previous video also, that the magnetic field acting on the arms, that is PQ, QR, RS and SP, only in the two arms SP and QR the force will be there, and in the other two arms PQ and RS the force won't be there. Actually they will be cancelling each other. F1 and F3 will cancel each other because they will be acting in the same line. The force F2 and F4, these two forces will be responsible to for the torque which will rotate the rectangular coil. Now this value of force is given by F1 as well as F2 as well as F4 will be given by BIL sin theta. That is the formula for force acting on a current carrying conductor placed in a magnetic field. So we can find the value of F2 and F4, which will be B is the magnetic field, I is the current, the length here is B. So to BIB sin 90, sin 90 is 1. So BIB is the force here for F4 as well as for F2. The direction F4 and F2 can be determined by using the Fleming's left hand rule. Now here you can see, if we take a top view, that is, we will see PQ and the force F4 and F2 in such a way that the perpendicular distance, because we are going to find the value of torque which will act on the rectangular coil as we have done in previously also. So the perpendicular distance between the two forces F2 and F4 is given by A sin theta. So if it is A sin theta, then the value of torque will be given by force into perpendicular distance. Force is BIB, or we can write I small b into B, capital B, which is the magnetic field, into the N. Value N represents the total number of turns. So the total force will be given by NIBB into A sin the value of theta. Since we know that the magnetic field is always perpendicular to the surface, so to the normal direction it makes an angle of 90 degrees. So theta will be 90 degrees. So we'll put sin 90 here. So it becomes NIB into AB, and AB represents the area. So the value of torque is given by NIBA. Now, if the value of torque is given by NIBA, then because of this torque, the rectangular coil will rotate, and since it is hanging by means of a phosphor bronze strip, that will experience a restoring torque in the opposite direction. And suppose for a torque, if the rotation is alpha, so the restoring torque on the which develops on the phosphor bronze strip will be directly proportional to the twist. More is the twist, more will be the restoring torque. A constant term we take K, which is called torsion constant, which gives the value of unit torque for unit twist. So for alpha twist or the alpha rotation, alpha angle rotation, the restoring torque will be given by K alpha. Okay, so we have the value of restoring torque, we have the value of rotating torque. So when the rectangular coil will be in equilibrium, rotating torque and the deflecting torque, that is restoring torque, will be equal. So restoring torque, we are writing it as K alpha, and the torque which deflects it is given by NIBA. So the value of alpha, or the twist, is given by alpha is equal to NBA by K into I. So what we can say is that the angle by which it is deflected is directly proportional to the value of current, because N, B, A and K all are constant quantity. N is the number of turns, B is the magnetic field applied, A is the area, and K is the constant, torsion constant. So in this way we find the value of current. The value of current will be given by K by NBA into alpha, which is written as G into alpha, where K by NBA is known as galvanometer constant, so it is given by capital G. The factor here, K by NBA, this is also very important. So it is called galvanometer constant or current reduction factor. So I hope this is very clear to you. I'll just repeat the basic thing here which you need to understand, that when a rectangular coil, when current passes through the rectangular coil, it experiences a torque, and since it is hanging by means of a phosphor bronze strip, that strip will experience a restoring torque. A time comes, equilibrium, when the restoring torque becomes equal to the deflecting torque. Deflecting torque we have calculated the value here, and the restoring torque we have calculated the value here. Where K is the constant, it is the restoring torque per unit twist. So for alpha twist it is K alpha. So the deflecting torque and the restoring torque when becomes equal, the rectangular coil will stop there, and then we will say that the deflection will give you the value of current. So I hope this is clear to you.